Okay, and then yeah, we'll put the talks on the website. So Emza, you can link it to your page if you want to or something.
Will do. Thanks.
And so for the community statement, we follow 3 kind of guidelines. And so the first one's we're all learning. And so some things might be obvious to some people and not so obvious to others. And so please feel free to ask questions, make use of the chat. Emzi, I don't know if you can if you can see the chat, but if not, you know, either Alex or I will kind of jump in and ask these questions. Second one is everyone has something to contribute. So we are all, you know, fanatics of combinatorics, but we approach it differently. And so please feel free to share any connections through the chat, or if you have any questions, we can either the speaker will have an answer or we can try to find an answer together. And then the last one is just to remind everybody that no one has all the answers. And so not even the speaker. And so sometimes we'll get stuck, but there are brilliant minds here. And so I'm sure we can figure out an answer, or at least someone to ask the questions to. And with that, I am very happy to welcome Amzi Jeffs from the University of Washington. And he'll be talking to us about convex codes, realizations, minors, and embedding dimensions. So let's welcome Amzi.
Cool, thanks so much for having me. And thanks everybody for coming to hear this talk. I'm excited to give it. I like to give these talks because I get to show a lot of cool pictures and yeah, tell people about open problems and all sorts of fun things. Yeah, there's a lot of words in this title, but we'll sort of get to them in sequence, maybe not in this exact order, but we'll get there. And yeah, I guess let's just get right into it. The first thing that I want to talk about is sort of what a convex code is and why we would care about them. This is kind of the introductory sort of framework portion of the talk. And the general question that we're going to try and answer throughout this talk, and you know, in this field in general, is stated quite vaguely on this slide, but the general idea is how can we arrange convex sets in Euclidean space? And specifically, how can they intersect and cover each other? And so this sounds pretty mathematically well motivated. It turns out that the original motivation for the version of this question that I'm going to talk about is actually neuroscientific as well. So if you've heard of place cells at all, these are cells in the brains of mammals. They get studied in rats a lot. And these cells have a really kind of remarkable behavior that they're active in a certain convex-ish, anyways, region in an animal's environment. So like this left picture here, we have a rat. We're looking top down. It's running around. Each color corresponds to a neuron. So for example, the yellow neuron is active kind of in the center of this rat's enclosure. And, you know, likewise, the red one in the bottom right, and so on. And so, yeah, if we want to understand what's going on with these neurons and how they kind of encode the animal's environment, like a map of it, well, we better understand how these approximately convex anyways, regions can overlap each other. And of course, you can do this in 3 dimensions as well. That's the picture on the right. They have this wild 3D maze that this rat with a little transponder attached to its head is running through. And so there's a link at the bottom of the slide where you can read a bit more about this if the biology is interesting to you. But of course, mathematically, this is pretty natural to think about as well. If you are interested in discrete geometry, nerve complexes, polytopes, hyperplane arrangements, Helly's theorem is another kind of example of understanding how convex sets can be arranged. These are all kind of things that motivate this question as well. And there's a nice 2011 survey paper by Martin Tanzer that talks a bit about, you know, one way to approach this question. And a lot of the past results, there's a link to that at the bottom of the slide. And that's where I stole these pictures from. Okay. So this is a vague statement at the top of this slide. Let's try to make it a little bit more precise. And before I do that, maybe I'll just remind us what convex sets actually are, so we're all on the same page with that. Pretty simple definition. A convex set is just any set in Euclidean space where if I take 2 points and draw a line between them in the set, that line actually stays in the set. So here's a couple convex sets in R2. One is this kind of skewed hexagon thing. One is a quarter of a circle, or a quarter of a disk, I guess I should say. And convex sets have some important features. We don't need to know too much about them for this talk, except a couple things I will use. You can always find supporting half spaces for convex sets. You can take a hyperplane and slide it right up to the boundary of your convex set. I've done this one for each of these sets with the red and the blue line are these supporting half spaces in R2. And then if I have disjoint convex sets, a nice property is that I can always find a hyperplane that separates them. I can put a hyperplane between them. Okay. So if I want to understand how to arrange convex sets or what arrangements are possible, I need some combinatorial way to record information about an arrangement of sets. And the thing I'm going to use is actually very general. I'm just going to use a code. And so that's any subset of the power set on the set 1 through n, which I'll denote bracket n. And just because of the motivation for this, I'm in the habit of calling indices 1 through n neurons. That's going to sound kind of weird, but if I ever say neuron in this talk, that's all I mean is a number between 1 and n. And elements of a code word, I'll call those code words. I'll often partially order the code words by inclusion, so we can talk about things like maximal code words, for example. And then finally, every code has an associated simplicial complex, which is just the collection of all the subsets of code words. Okay, so that's a lot of words, but here's an example. Here's a code C. This code has 6 code words. I have 3 neurons, 1, 2, and 3. So for example, the 1, 2, 3 here is not 123, it's just 1, 2, 3, but I've compacted my notation a little bit. And then the simplicial complex of this code, well, it's just a 2 simplex. I only have 1 maximal code word, 1, 2, 3. Okay, so these are my combinatorial objects of codes. Very, very general, kind of, they feel almost arbitrary, but that's what we're going to use. And I want to use them to understand arrangements of convex sets. So if I have such an arrangement, let's just say U1 through UN, convex sets in RD, I'm always going to assume they're either all open or all closed. So I want to restrict just topologically to those types of sets.
I have a question.
Yeah.
Do your, I think it was code words you said, do those have to be closed under inclusion?
No, so codes are more general than simplicial complexes. Yes.
Okay, thanks.
Yeah, and that's actually going to be really important. Yeah. Yeah, so if I have a collection of sets, I want to define an associated code that tells me how the sets intersect. Okay, so there's a lot of symbols here, but I'll just say verbally what this is. I label all my points in space according to which sets the point lies in. I collect all those labels, and I'm going to say that that's the code associated to my collection of sets. And I'll draw you a picture in just a second. One final piece of vocabulary, I'll call this collection a realization of the code. And if it's a collection of open sets, I'll call it an open realization, and closed realization likewise. Okay, so here's a realization. I have 3 sets in R2, they're convex. There's kind of these ovals, and the code that these give rise to is actually the code we looked at on the previous slide. So for example, the code word 2, 3 comes from this highlighted gray area where I'm in sets 2 and 3, but I'm not in set 1. And likewise, for example, the code word 3 comes from this region on the right where I'm in set 3, but none of the other sets. The empty set comes from somewhere outside my sets, and so on. Okay, great. And what I want to understand is if you hand me a code, can I find a realization of it? Can I draw some sets that would give rise to that code? And to kind of get a handle on that question and make it a little bit more structured, the thing I'm going to talk about is an open embedding dimension of a code. So this is just the smallest dimension where I can find an open realization of the code with convex sets. And if I can't find one in any dimension, I'll say it's just infinity by convention. But this is capturing how realizable a given code is. And I could do the same thing for closed sets and call it a closed embedding dimension. That's fine as well. Smallest dimension where I can find a closed realization. And so here's this realization from the previous slide. This tells us that so it could be open sets or closed sets. I can replace these sets with their interiors or closures, and that doesn't change the code. So this tells me the open and closed embedding dimension is not larger than 2, I can find a realization in R2. But actually, I could do better. I could squash these into intervals, and then I would get a realization in R1. So here the open and closed embedding dimensions are both equal to 1. And now at this point, I'm going to ask for some audience participation. This goes differently in different audiences, but I'll try it. I think it's good. Here's a code. It's a different code than the one we've been looking at. And I'm going to ask you a question, which is, can you find me a realization, open or closed, whatever you feel like, in R2? And then how about in R1? So I'll give folks a second to think about that. And if somebody feels like they can draw this code in R2, maybe tell me and describe what you would draw.
What comes to mind is 3 circles and then a big circle containing them. Does that work?
You say 3 circles and a big circle containing it?
Yeah.
So there is one issue with that, which is that the total number of sets should end up being exactly 3, because I have 3 indices. So I will only need 3 sets in my drawing.
You kind of want some kind of sunflower looking thing where you've got like a...
You've paid attention to the title of the talk.
Okay.
Yeah, I agree. And so here's, actually, I don't even need to draw it. I can just skip to the next part. So you need 3 things that overlap each other somewhere. The 1, 2, 3 code word tells you your 3 sets need to overlap somewhere. And then 1, 2, and 3, well, outside of that overlap, only one of the sets should show up at once. So here is a drawing of this. U2, for example, is this left piece where it's the square where they all overlap, and then this other kind of flap that's coming off. Right, okay, so this is a realization in R2, and I can't draw one in R1. I kind of need another direction to have a flap come off of. So here the open and closed embedding dimensions are both equal to 2. Cool, thank you for bearing with me with the audience participation. And one final example to convince you that this question is kind of non-trivial, or that maybe this infinity convention I have is actually something I need. Here's another code, again, 3 indices, 3 neurons. And I claim I can't draw this in any dimension whatsoever. And why is that? Well, the code is telling me that the set U2, if I tried to draw it, would be covered by U1 and U3, because 2 only ever appears with 1 or 3. And then 1 and 3 don't appear together, so they're disjoint. And so U2 would be the disjoint union of 2, let's say, open convex sets. Well, that means U2 cannot be open and convex itself. It can't even be connected. So this is kind of a topological problem that's happening here. So here the open and closed embedding dimensions are both infinite. Okay, so those are some kind of introductory examples. And the main thing we're going to look at in this talk is understanding these open and closed embedding dimensions for codes and sort of what's going on with them. And here's kind of the big conceptual picture we can have in the back of our head. We have our geometric objects on the left, our collections of convex sets. And then on the right, we have our combinatorial objects, which are codes. For any collection of sets, I know how to make a code. And for any code, I can try to draw a collection of sets, but that's a little bit more mysterious. It's harder to find. It's harder to go from right to left. And the overall question, yeah, if we have a code on n neurons, how does the open and closed embedding dimensions relate to each other? And how does that relate to the number of neurons as well? Comparing these numbers is kind of the main play that we'll be making. And I'll just say this question was first posed sort of formally in 2013. There's been a ton of really interesting work since then that I unfortunately don't have time to talk too much about. But I'll be citing a lot of papers throughout this talk, and I'll have a list of them at the end. And that I think is a good sampling if you are interested in reading up on this at all.
Who are CI, V, and Y?
So this is Karina Kurto, Vladimir Itzkov, I forget his first name, Velis Cuba, and Nora Youngs. And Nora Youngs is a student of Karina Kurto, I think, at the time this paper was published.
Hi, I have a question.
Yeah, please.
So when we consider convex codes, do we know if a sub-collection of, let's say, nice convex sets is enough to consider all convex codes? let's say for instance, spheres and cuboids or their d-dimensional analogs, are they going to be enough, or we don't
Yeah,
know?
this is a really good question. And maybe the most general nice family you'd want to try and use is, instead of general convex sets, you'd want to reduce to the case of either polytopes or their interiors. And we don't even know that we can do that, unfortunately. That's kind of frustratingly, surprisingly difficult problem that people have not been able to figure out.
I-
Yeah, I mean, I think it would be interesting to look at, let's say, codes realizable with axis parallel boxes or something. You could do that, and that would be interesting, but it would be a proper subclass of all convex codes.
Okay.
Yeah. Okay, cool. So this is the picture we're working with. Let's jump into the rest of this talk. I'll tell you a nice discrete geometry theorem. I'll tell you how to apply it to this problem. And then hopefully at the end, I'll have time to tell you about sort of the big picture and zoom out a little bit more and give some more conceptual context. Cool, yeah, so we're gonna start by looking at sunflowers. Now we're going to get into this discrete geometry theorem. We'll take a little bit of a detour, and it won't seem like we're talking too much about codes, but then we'll see if this is important. So I want to look at certain arrangements of convex sets called K-flexible sunflowers. And so what is this? So it's just a collection of sets where all the sets meet in a central region, and outside of that region, no more than K of my convex sets can overlap at once. And so I can express this in terms of the code of my collection as saying I have the code word 1 through n, all my sets overlap, and the rest of the code words have size no larger than K. And I'll throw the empty set in there as well, just for safety's sake. And I'll call the sets in my collection petals. I'll call the region where they all intersect each other the center of my sunflower. And the notation I'm using here, if I have a set of indices sigma, u sub sigma is just the intersection of all the ui's with I and sigma. So that's what u sub brackets n means. And if k is 1, I'll just call such an arrangement a sunflower. So here's this drawing we did in the sort of beginning of the talk. It's a sunflower with 3 petals. K is equal to 1. We're working in R2. Here's a drawing of a similar sunflower in R3. I have 3 petals again. K is equal to 1. And here's an example with K equals 2 in R2, and I have 5 petals here. And we see that the center is just this kind of highlighted gray area. But then outside of that gray area, no more than 2 of my sets can overlap at once. Okay, so these are the objects I'm interested in looking at, and I will tell you on the next slide why I'm interested in looking at them. So it turns out that these sunflowers, as long as we're working with open sets, actually have a lot of structure geometrically. So the first observation of this was in a 2017 paper, and the result there is that if I have 3 petals in R2 and I choose a point from each petal, the convex hull of those points, that triangle, has to hit the center of my sunflower. Another way to say this is I can't slice through 3 petals with a line without hitting the center of my sunflower. And I'm going to tell you 2 generalizations of this theorem, and there's going to be a lot of text on this slide, but then I'll draw some pictures, which I hope will kind of illuminate what's going on. So this was 3 petals in R2. It turns out the same thing is true if you move up to D+1 petals in RD. As long as you have enough petals larger than the dimension, if you choose a point from each petal and take the convex hull, you're going to hit the center. And then we can introduce this K parameter, and the cost of doing so is that now the number of petals I need has to be larger than D times K. So it was larger than D when K is equal to 1, and in general has to be larger than D times K. Okay, so these are just generalizations of each other, and let me draw a picture to actually make some sense of this. Here's the first case. I have 3 petals in R2, all open sets. My center is this kind of triangle area. Here's a choice of some points, 1 from each petal, and indeed the convex hull has to intersect the center of my sunflower. Here's the example I drew before with K is equal to 2 and N is equal to 5. So 5 is larger than 2 times 2. Again, this result should hold. And here's a choice of points, 1 from each petal. Convex hull, again, intersects the center of my sunflower. And maybe the final thing to notice is this really doesn't work if I'm not working with open sets. here's a sunflower with 3 petals in R2 of closed sets, just line segments that meet at a point. And of course, if I choose some points from each petal and take the convex hull, well, I don't have to hit that point that they all meet at. Okay, so this is somehow special to open sets.
So quick question.
Yeah.
If the interior of the center is non-empty, can we say that the intersection with the interior itself is non-empty?
I believe that you could say that, and I don't think it would be too hard. I think you would just replace your sets with their interiors. Maybe you'd have to wiggle things a little bit and the result would hold. So if things are full dimensional, this type of result, I think should just be okay.
I see.
Yeah. Cool. So here's a reminder of what the result actually states. If I have more petals than d times k, take the convex hull of points, 1 from each petal, I have to hit the center. And I have heard that every good talk includes one proof, so I'd like to sketch a proof of this for you in the next few slides. I'll do it informally, but I think it's kind of interesting to see what's going on in the background here. So let's suppose this result doesn't hold. Here I'm going to work with just a sketch of how it would look in R3 with k is equal to 2 and n is equal to 7. So here 7 is larger than 2 times 3, so the result should hold. And here's the center of my sunflower on the left. I have my petals coming off of it, very roughly going off to the right. And if the result didn't hold, I could choose points, 1 from each petal, and the convex hull of those points would not hit the center of my sunflower, something like this, where the right side, this kind of orange area, is the convex hull of my chosen points. Now I have disjoint convex sets. Let's put a hyperplane between them, in this case, just a plane in R3. And what I can do is take, let's say, P1 and draw a line from P1 to the center of my sunflower. It'll cross that hyperplane. And so why not replace P1 with the point where it crosses the hyperplane? And let's do this for all my points. So now I've reduced to the case where all my points lie in a codimension 1 subspace of RD. And it's actually, I've cooked up the numbers basically so that the number of points here allows me to apply a result called Fairberg's theorem, which is a very sort of classical discrete geometry result. It lets me partition all my points into k+1 parts, so here are 3 parts, such that I can choose a common point in the convex hull of all the parts. So I can find this point P, which is in the convex hull of the red points, the blue points, and the green points.
Sorry, Amzi, and
Yeah.
you said, I think you said it, but I kind of missed it. How did you choose these points, or are they just arbitrarily?
Yeah, so the points are, I'm assuming that their convex hull doesn't hit the center. That's all I'm assuming. And then I project them onto a codimension 1 subspace so that I can work in a smaller dimension and apply Fairberg's theorem.
Awesome.
But they're still, I guess the important thing about the projection is they're still far away from the center, a positive distance away. And this hyperplane is a positive distance away from the center. Yeah. So I am brushing some details under the rug that I can pull this hyperplane away a little bit, but you can trust me. So I've chosen a point that's in the convex hull of each of the parts. And the final thing I have to prove, and this does require a little bit of kind of fiddling around, but you can do it, is that most of the supporting half spaces for the center have to contain at least one of these parts in my partition. This has to do with the K parameter. There's a way to kind of geometrically prove this. And in particular, most of a dense subset of the supporting half spaces to my center must contain this point P. And that's a contradiction because then P would be very close to the center, but I've constructed it so that it has positive distance away. So that's maybe the reason I wanted to present this proof, is just that to say that the sort of main ingredient going into this is Fairberg's theorem, which is kind of a classical type of discrete geometry result. It's hidden under the hood, I guess. Okay, so that's this theorem. I've put it up on the slide again to remind us of what we just proved. If all that's kind of mysterious, don't worry too much, because the rest of the talk, I'll just be trying to apply this theorem in a few different cases. But before I get into that, maybe I'll pause for a couple seconds just in case anybody has any questions.
I have a question here.
Yeah.
So some of the language you're using here sounds kind of probabilistic. Can I ask if any probabilistic methods were part of your proof?
I think that's a really underexplored area in convex codes. And this proof, so actually, I mean, if I sound probabilistic, it's probably mostly because I'm just waving my hands in this talk to avoid talking about the details. The proof is like completely, I don't know, concrete and sort of specific, I guess. But I think there is a lot of probability type arguments that could be used very fruitfully in convex codes, but just have not been yet. Yeah.
Thanks.
Okay, so let me tell you what this theorem has to do with convex codes and why it's kind of important. There's actually a lot of applications of it. So I think I'm up to like 6 or 7 now different results you can prove with this about codes. But I'll tell you maybe 2 results. One is the very first, most basic one, and then I'll tell you a more recent one that I think is kind of, I don't know, exciting and interesting. So this 2017, the very first version of this theorem that I mentioned, the importance of using this theorem in that case is that you can find a code that is realizable with closed sets, but not open sets. And so here's what that code is, but let me make you a drawing of closed sets that realize it. The important feature of this code is that the sets U1, U2, and U3, so here in red, green, and blue, those have to form a sunflower. And the rest of the sets are constructed so that no matter how you try to realize your code, you're going to slice through all the petals of that sunflower with a line. And we know we can't do that if these are consisting of open sets in R2. And the way we've constructed this code allows us to reduce to the R2 case. So I can't draw this with open sets no matter what dimension I'm in, but I can draw it with closed sets in R2, which is already kind of, there's no reason for us to necessarily believe right away that there's a difference between using closed and open sets for codes, but this tells us there's actually a pretty significant difference. Okay, so that's one application. To tell you about another one, I'll need to introduce a few objects to talk about. The first will be a family of codes that I'll call S sub n for any, let's say, n greater than or equal to 1. And what is this code? Well, I'm going to have every singleton code word. I'm going to have every pair that contains the neuron n plus 1. I'll have the empty set, and I'll have the set 1 through n. And so this theorem from before, sort of an equivalent version, at least in the k equals 1 case, is that the open embedding dimension of this Sn code is actually equal to n. And the reason for this, so these, in a realization, if you tried to draw one, U1 through UN would have to form a sunflower, because I have the code word n, they all meet somewhere, and the rest of the code words that involve 1 through n are just singleton sets, so they don't meet outside of that region. And then this n plus first set is constructed to touch every single petal, but not touch the center. And this theorem that we had before basically tells us that's impossible unless the dimension is at least the number of petals. And of course, that tells you one direction of the inequality. That tells you the open dimension is at least n. To show that it's no more than n, I have to construct a realization. Here's a picture of how that would look in the case n equals 3, for example. I can just thicken all of my coordinate axes into sort of rectangular prisms, and then slice through them with some hyperplane that's far away from the origin. And that gives me an open realization. And so here, maybe I should have labeled this, but I can now. So this would be like U1, U2, U3, and then U4 is my set that slices through all the petals. And you can kind of imagine how to generalize that in higher dimensions. Okay, so this is not the application quite yet. I mean, it is sort of an application. It's a result we can prove using this theorem, but it's not the punchline. To tell you the punchline, I need to slightly generalize this family of codes Sn. If you hand me a simplicial complex on n vertices, or n, I guess I'm calling them neurons, but whatever. I'm going to form a code S sub delta. And what is it? Well, I take the join of this simplicial complex with some new neuron, new vertex, and then I add one code word 1 through n. So I have 3 types of code word in S delta. I have faces of my simplicial complex, faces union my new neuron, and then I have this code word 1 through n. And this does generalize the S delta family, or the SM family. SM is the, oh, sorry, I should say SN is equal to S delta, where delta is just N disjoint vertices. Okay, but what's the relevance of this S delta thing? Why do we want to make this generalization? Well, it turns out that the number of facets, let's call it M in delta, is important. It's going to be potentially large relative to N. And it turns out that if I have a realization of S delta with delta having M facets, I can use it to build a realization of SM. And I won't justify exactly how that works. I'll tell you if I have time later in the talk, kind of how what I mean by build a realization. But the importance of this is that if delta has at least 2 facets, let's say M is larger than or equal to 2, then I can find the open embedding dimension of S delta, and it's actually equal to M. So if I can use a realization of S delta to build one of SM, well, I know the open dimension of S delta has to be at least the open dimension of SM, which I mentioned before is equal to M. And to get the inequality in the other direction, there are some results in the literature that let me construct a realization of S delta in the appropriate dimension. Okay, so here's the punchline that I wanted to get to. So I mentioned that M can be very large relative to N, right? So this tells us that the open embedding dimension of a code can actually be larger than the number of neurons that code is on. And so this is, this is something that was kind of unclear and wasn't known at all before, but the open embedding dimension can grow exponentially as compared to the number of neurons. So I've just restated that at the top of this slide. And I'll tell you maybe 3 reasons why this is actually kind of surprising. So one, if we think back to the neuroscience that motivates this, this is telling us that our mathematical model of these place cells is indicating that in theory, a number of neurons N can recognize a dimension that's larger than the number of neurons, even exponentially larger. So somehow place cells in this model, I mean, who knows if this happens in real life or in an experimental context, but in this model anyways, the neurons can be very efficient at recognizing dimension. This also fails completely for closed sets, at least with the families of examples we know. For these S delta codes in particular, the closed embedding dimension we can prove is linear in the number of neurons. It's no more than N-1, so it's quite small, or at least relative to the open embedding dimension. So this is another gap between closed and open sets. And the other thing too, so there's classical kind of ideas of studying nerve complexes and things like this, where you only, instead of looking at codes, you only look at simplicial complexes of codes. And in that context, this linear bound holds as well. So this kind of, these previous ways of understanding intersections of convex sets actually don't capture this phenomenon. We need codes to capture it. And so codes, maybe the moral of the story is that codes are very granular. They can capture quite a lot of information about an arrangement of sets in a way that's very strictly different than what we were able to capture before. And so this is, I mean, it's an advantage or a disadvantage depending on how you think about it. For a code, you need to keep track of a lot more information. There's a lot more, nitty-gritty stuff to work with. But that cost actually does pay off in certain circumstances. Okay, so I think that's the punchline I wanted to get to. And in the rest of the talk, I'll tell you some kind of background context and zoom out a little bit. But before I do that, are there any questions? Okay, cool. So there's one word in the title of my talk that I haven't told you about yet, which is minors of codes. So I've told you about realizations and embedding dimensions, convex codes. Let me tell you what a minor actually is. And I'm going to start with some combinatorial definitions that don't seem very well motivated and might be kind of opaque, but let's do it. We'll see that they're important. So let's say I have a code on N neurons and I have some set of neurons, sigma. I'll say the trunk of sigma in C is just some collection of code words. It's the collection of code words that contain sigma. And here's the notation I'll use, tk sub c of sigma. So this is, if you're familiar with simplicial complexes, this is behaving like an open star in a simplicial complex. And the reason that I want to look at these trunks is that the code words in a trunk correspond to points in a set U sigma, where, remember, U sigma is the intersection of all the UIs with I and sigma. And of course, if all the UIs are open and convex, well, so is U sigma. And so these trunks kind of capture things happening in a convex region in my realization, if I have a realization. Okay, but I'm going to keep being abstract for a minute here. I'll say that a function between two codes is a morphism if the preimage of a trunk is a trunk, sort of like a continuous map, but not. It is distinct from being a continuous map. There's not an underlying topology we can use to define these. But okay, here's a definition of some type of morphism. You can check that, you know, the identity is a morphism, compositions are morphisms, and so on. So we get like a category and things like that. But the thing I want to define for us is a notion of minors. And I'll say one code is a minor of another if there's a surjective morphism from the top code to the minor code. And if I'm using the word minor, okay, if you're familiar with things like matroid minors or graph minors, you know, you hope that there's a nice partially ordered set of all these minors and that it has cool behavior. And indeed, that's the case. Let me actually just draw the first few kind of pieces of this set. It turns out that it's ranked. So this partially ordered set of all codes partially ordered by minors is ranked. There's only one rank 0 code, which is the code whose only code word is the empty set. Above that, there's also only one code at rank 1 that has 2 code words, 1 and empty set. Of course, all this is like up to isomorphism, but don't worry too much about that. Once we get to rank 2, we have 2 codes. Here they are. One of them is just a nice little chain, 1, 2, 1 empty set. And I'm drawing these codes as Hasse diagrams. So here are this 1, 2, 1 empty set. Those are my 3 code words, partially ordered by inclusion. The other code I have here is 2 singleton sets in the empty set. Okay, at rank 3, things get a little bit more complicated. And then at rank 4, they get much more complicated, and we can't really draw a picture beyond that, but here's a picture anyways. Anyways, we can, this is very concrete. I mean, just to say that we can do this, there is, you know, since it's all combinatorial, we can kind of compute things by brute force and draw some pictures and look at what's going on. But this isn't the most illuminating picture, especially if I care about things like open embedding dimension, for example. I haven't told you at all what this has to do with that. So maybe let me do that. And the definition I'm going to need is if I have a realization of sets or of a code consisting of sets U1 through UN, I can make a new realization. I can build a new realization by collecting some of these sets and their intersections. So I'll define a realization V, a derived realization, I'll call it, where I have sets V1 up to V, let's say M, which might not be equal to N. And each Vj is an intersection of the various UIs. And here's a picture to make this kind of concrete. I have my realization on the left, consisting of 4 sets. My derived realization is on the right, consisting of 5 sets. And so here, for example, V1, is the intersection of U1 and U2, because I've chosen sigma 1 to be 1, 2. Okay, so a little bit opaque, but the important thing to notice is that if U1 through UN are convex and open, well, so are all the V sets. So this derived realization is still consisting of convex open sets. And it turns out these derived realizations are the same thing as minors of a code. So they're the geometric version of minors of a code. If I have a minor of a code, if let's say I have a code and a realization, then a minor of a code corresponds to some derived realization and vice versa. So in particular, if I have a convex code, all of its minors are going to be convex as well, and even preserving the dimension that I can realize my code in. And so this actually does help us understand geometry. I've thrown some abstract combinatorial stuff at you to define these minors, but the important feature of them is that open and closed embedding dimensions behave nicely in this partial order. If I have a minor, D is a minor of C, then the open or closed embedding dimension of D is no larger than that of C. So here's kind of a conceptual picture of what's going on. Let's say I have all my codes scattered around. I define minors so I can partially order them. So here each red dot is like a code. And then the result from the previous slide I just mentioned tells me that open and closed embedding dimension let me slice up this partial order into nice layers. So I have my codes with open embedding dimension 3 sitting above those with 2, 1, 0, etc. All of my non-convex codes are kind of an upward closed set. Convex codes in general are a down closed set in this partial order. So this is, again, kind of an analogy to graphs where things like, being planar is closed undertaking minors. So here being convex is closed undertaking minors. And let me explain, maybe in just the final couple minutes of my talk, what these SM and S delta codes have to do with each other in this context. So I said S delta can be used to build a realization of SM if delta has M facets. So what I really meant there is that I can find a derived realization, or in other words, SM is a minor of S delta. And so here's a picture of how that looks. If I collect all my S delta codes where delta has M facets, then in that collection, the unique minimal minor is this SM code. And these results about embedding dimension tell us that in this layer that we're sitting inside, this collection of all these S deltas really sits between open convex in RM and open convex in RM plus 1. They're right sandwiched in this layer here. So this isn't really telling us anything we didn't already know, but it is giving us a nice conceptual picture in our head of kind of how these things are laid out relative to each other and what relates to what. And I mentioned that the open embedding dimension can be exponential. So the reason for that is that the open and closed embedding dimensions, so here the open embedding dimension is behaving nicely with respect to minors. It only goes down as you go down in your partially ordered set of code minors, but the number of neurons in a code can actually go up. So this SM has many more neurons than these S delta codes, which is kind of surprising. The number of neurons seems like it shouldn't increase as you go down through minors, but it actually does, and even exponentially so. Okay, so that's kind of the big picture and tying in some of the results we talked about. Maybe in the final 2 minutes, I'll tell you a few open questions. So we saw that open embedding dimension can be larger than the number of neurons. Can the same be true for closed? We don't know. Probably yes. I mean, not for the codes we've looked at so far. I suspect the answer is yes here, but I don't have a family of examples yet. Maybe one day. Another thing we could try to do is characterize minors of simplicial complexes. It turns out these are exactly intersection closed codes where an intersection of 2 code words is a code word. Those are the minors of simplicial complexes, but understanding which simplicial complexes lie above a given code, intersection complete code, that's very much an open and I think potentially interesting problem. And then last thing I'll say, if you enjoyed the geometry in this talk, there's many more families of examples to kind of tinker around with. Here's a picture of sort of one family of examples where I don't know what's happening even beyond so here's T1 through T4. I know what T5 is. T6 and beyond is completely mysterious to me. So if you know how to figure things like this out, send me an email and we can talk. Okay, so I had some bonus slides, but I think in the interest of time, I will skip these ones. That's okay, they're optional. And I'll just end with some references and say, thank you for having me.
Awesome. Let's thank Amzi. Are there any questions for Amzi?
I have a question actually. So it seems like you use a strong coding theory vocabulary, talking about code words and all of that. Is there some kind of metric on your convex code to actually kind of create those code from coding theory?
That's also something that I think is underexplored. I guess I confess to not knowing much about coding theory at all, unfortunately, even though I've gotten used to using those words. For example, like error correcting codes and things like that, I just don't know about. it's a little bit, I mean, I guess the difficulty with making that connection, I think, is that here the codes I'm looking at, I'm not thinking about the code itself as geometric at all. Whereas in coding theory, you want to understand like the geometry of how the code words sit as vectors in space, I guess, is my understanding. Yeah, whereas my codes kind of are just a combinatorial object to record the geometry that lives somewhere else. So that's not to say that we couldn't make some interesting connections, but I think that unfortunately I'm not equipped to do it yet. And I don't think anybody else has quite been able to do that yet. But
Yeah. I was wondering, yeah. Thank you.
Yeah.
I have a couple of questions. One is just if you could go back one slide.
Yes. Yeah, I had two pages of references, but most of this talk comes from the paper at the top from 2019.
So then the other question is, you had this graded post set with all the ranks. Do you know how many things there are of each rank?
Not at all, no. And that's, I mean, yeah, this thing has basically just, I guess this partial order is kind of unfortunate because it's appeared in, I think now, 3 or 4 different papers, and I'm writing my thesis, and finally in my thesis, I think I've nailed down the definition that we want to use, whereas in those other papers, it kind of varies. So yeah, so people have not, I think, quite gotten their teeth into the structure of it as a post set, except to say, so I guess some questions I would have would be, for example, if you look at an interval in that post set, does it have to be unimodal? Seems like it should be, but I don't know. I think there's other questions you could ask like that. I mean, we know it's not a lattice. I know that there are infinite anti-chains, unlike the post set of graph miners. So that's kind of a, I mean, interesting but negative result. So there's a few things we can say, but I think, I mean, the numerics or the combinatorics of this post set, I think, are very a wide open thing to investigate.
Yeah, I have a comment about the possible relation to traditional codes. What's of interest in traditional codes is the Hamming distance between code words. Which is I guess the size of the complement of the symmetric difference. The number of zeros and ones that have to be exchanged to convert one code word to another. So it's a measure of how similar how similar any two code words can be. And the goal is the better the code, the larger is the minimum similarity. Just a thought about what the geometry, the kind of geometry that's relevant in coding theory.
Yeah, but then you can define, if you start with different vector spaces, you can define different metrics.
Well, no, it's the vector spaces are used to construct codes that are easy to construct and easy to decode in practice.
Yeah, but you could define certain metrics. Vector spaces and.
Well, it happens that in a linear code, the Hamming distance, the minimum Hamming distance, is the is the Hamming size, the number of ones in a minimum sized vector of the code. That's because you could take the difference of two vectors mod 2 and but in general it's harder to work with our general, not necessarily linear codes. So there may be little that's going on here that's related to what people do with linear codes. But the original problem of coding theory might be more relevant to that. Just a somewhat uninformed thought. Yeah.
Oh yeah, thanks for that. And I think something else I'm interested in, but I haven't made any progress on yet, is So this partial order on codes, I wonder what it means in the case of, if you think about codes, yeah, from a coding theory perspective or from some other perspective, like, does this notion of minors, I mean, I've constructed it to be useful to convex codes. Does it tell us anything in these other contexts? I don't know. I'd be very interested to think about that. Or, I mean, yeah, just the families of kind of esoteric examples that exist in other fields would be, I think, very useful to try and, you know, draw some realizations of and see what happens.
Wait, so did you say you were able to write down a nice definition of what this post-it, or not?
Yeah, I guess I can. Let me think about how to state that. So, I mean, this definition that's here of having a surjective morphism, that's very concrete. And I mean, morphisms are actually there's a nice combinatorial way to say what they are, and they're not too bad to work with. On the other hand, this doesn't exactly, if I hand you two codes, it doesn't really give you an efficient test for if one is a minor of the other, for example. But I mean, I think this definition that I have at the bottom of this slide, that is the definition I'm using. And I think it's the right one or something. Yeah.
Yeah. Well,
The other thing I guess I'll say, one thing that is understood in this post set is the covering relation. I have a complete characterization of that. And
okay.
It's
Yeah, I think
not
that
too bad.
So I was just curious because whenever I see a post set, I'm just thinking about like order polytopes. And so I'm thinking if maybe, you know, if you were able to describe this post set nicely, then is it even worth studying, you know, the order polytope of this post set?
I have no idea, but I would love to know.
Awesome. Are there any other questions for Amzi?
Yeah. So on this picture, what's the difference between the one that you used dotted lines and the other ones that are not dotted?
Yeah, I didn't explain that at all. So the dotted line codes, the ones that are not dotted lines are the intersection complete codes. They're codes that are closed under intersections of code words. So here, for example, I don't know, this one, 1, 2, actually, I don't know if you can see my mouse. I'll draw this. So this one, you can check if you intersect two code words, you get a code word back. Whereas here, the intersection of 1, 2 and 1, 3 is 1, which is missing. The dotted lines are not intersection complete.
I think there's a typo in the fourth row from the bottom. The second code from the left is missing. What below that? Just below that. Right? There's no 3.
That's okay. It's a code on only 2 neurons.
Oh, okay. Good.
Yeah.
Thanks. Yeah.
Yeah.
Huh. Okay.
I think Eric.
Another quick question. Sorry.
Go ahead, Venkatesh.
Yeah. So could we say something more about a convex code in terms of its simplicial complex?
That's a good question. Yeah. And that's, so if you think about nerve complexes, the simplicial complex of a code is exactly that. So those are basically the simplicial complex of a code. If that's the only information you care about, this is something that's been well studied since like the 70s or so, maybe even earlier. And in that context, you get some bounds, you get some information, but you do lose, for example, you lose this exponential type of result that I had. You can't do that if you only care about the nerve. But the simplicial complex is important because you can do things like recognize, for example, there's a notion of like a quote unquote local obstruction to convexity where you have some kind of like violation of the nerve theorem, and you can find that in like a topological way using the simplicial complex. So it is something that people have worked on and tried to study. But it also strictly loses information, I guess. It's an incomplete picture, I guess. Does that answer your question?
Yeah, thanks.
Okay, cool.
Sorry, I cut off Eric. So Eric, go ahead and ask your question.
Yeah. Do you know how much information the post set contains about the category? Like it's a flattening, right? We pretend there's only one morphism.
Yes.
But is it equivalent? Do you know anything like this?
Oh, this is a good question. So I think it can't be equivalent because you have things like inclusions of codes that just don't show up in this post set. I guess categorically, there's a few things that are known about, yeah, the category of codes. I mean, I've proven that it's finitely bicomplete, if that means something to you. We have limits of all finite diagrams and co-limits of all finite diagrams. And so, yeah, I guess you can prove some categorical things of that nature. You have like, you know, products and all that kind of stuff. And some of it behaves nicely relative to the geometry, but the category structure has not helped me very much to understand the geometry, so I haven't used it very much. I think that's, I don't know, if you're interested in the category theory for other reasons, I think there's plenty to develop there, but yeah, it's not been delved into super deeply.
Thank you.
I think in your terminology, there'd be many morphisms coming out of one code. Yeah,
Yes.
what from your definition of morphism is based on what some subset of the, yeah.
Definitely, yes. Many, if you hand me two codes, they have many morphisms between them. And I think even up to an appropriate notion of equivalence, you should still have a lot of morphisms between codes.
Awesome. Do we have any last questions for Amzi?
I have one, but sorry, this is just silly. It might be nothing at all. So you were describing the behavior of neurons using a convex-ish language. Is it also possible that we can use a non-convex-ish language to describe neurons, or is it biologically speaking, neurons just didn't behave in the non-convex-ish way?
This is a really good question. And yeah, I'm glad you asked, because I think it gets at the fact that this model of these neurons is quite imperfect. And I mean, necessarily so, because if you're going to measure these things experimentally, you don't get a full picture of the convex set, you get some sampling of it. And that kind of goes back to Rowan's question, which is like, you know, maybe you don't understand the full code, but you do understand a sampling of it based on how the rat has moved through its space or something. And then what information can you reliably extract there? I think there's, you know, you could make statistical or probabilistic arguments that they're not the direction that I've pursued, just because I've been working in the geometry side of things. But I think the people who do the neuroscience would actually be quite interested if you had some nice statistical probabilistic kind of, you know, we can get this information reliably using this strategy type of thing. And in that context, I think you're right that you'd want to go slightly beyond convex sets, and you'd want to maybe loosen that and say something is close to being convex or something like that. Or maybe you're just getting a partial sample of a convex set and you have to define that mathematically somehow. I think that's very well motivated. Yeah, it's just not something I've done yet myself.
Awesome, great questions. So before we thank Amzi one more time, let me invite you again to next week's GOCC. And so next week, we'll have Jody McWhirter from Washington University in St. Louis, and she'll be talking to us about Ehrhart quasi-polynomials of Coxeter permutahedra. And so if that interests you, I hope that you join us next week. But without anything else, let's thank Amzi one more time.
All right, clap. Yeah.
Thanks for having me.